In all the questions we've talked about so far, we've always been concerned about individuals. For example, what's the probability that an individual person, randomly selected, has a weight less than 140 pounds? That's the first question. We've answered a bunch of those. The next step forward is to think about groups. For example, what's the probability that the average weight of a group of 20 people is less than 140 pounds? That's what you see in the second question here. Now, this is an important step forward for two reasons. First, it's going to let us answer some important practical questions. Right? Thinking about the weights of a group, for example. Have you ever gotten onto an elevator and seen a plaque up by the front panel that says something like maximum capacity 20 people? It's kind of an interesting thing to say. Obviously, you don't want to overload the elevator, but the cables don't care about the number of people in the car. They care about the total weight. Now, unfortunately, weight isn't a practical thing for people getting into the elevator to think about. You don't want to have to, take a survey of people's weights just to decide if someone needs to get off. Taking a head count, on the other hand, is quick and easy. So the maximum capacity is determined by thinking about whether or not the average weight of a group of a certain size will exceed the capacity of the cables. And second, this is going to be an important step toward being able to use the values taken from a group to make inferences about the entire population. Okay, so suppose we want to answer my question from the previous slide about a group of 20 men randomly selected from the population. Well, to do this, we need to think about all the possible groups of 20 men that we could choose from out of this population. Each of those 20-person samples is going to have an average weight. So what I need to know is how are those average weights distributed? For example, how many groups have an average weight of 120 versus 130 versus 140, etc. Right? The probability distribution that describes all the values of a statistic, like average weight, for samples of a given size is what we call a sampling distribution. And if we want to talk about a specific parameter, like the mean, right, then we could be more specific and talk about the sampling distribution of the sample means. And yes, I know the language gets a little repetitive, a little Byzantine, okay, but that's the kind of label that we use to describe this sort of thing. So to see what's going on in this kind of situation, I want to look at a specific example. Right, suppose I survey 3 families and ask them the number of children they have. Now, that's obviously an unrealistically small sample, right, for practical work, but I'm keeping this small so it's practical for us to do the calculations that are going to illustrate the more general result. Right, now, suppose that the answers I get are the numbers up here at the top, 1, 3, and 6. What I want to know is what's the average family size for families with 2 children. Right, well, to figure this out, I'm going to start by writing out all of the possible 2-family groups that I can get from this sample. So to do this, I'm going to assume that we're doing this with replacement, right? So first, it's possible for the one child family to be selected twice. And then I could get the 1 and the 3, or the 1 and the 6. All right, now how about the ones that start with 3? Well, I could get 3 and 1, and yes, I want to include that one. I know I got 1, 3 on there already, right? But I want to assume that the order I pick them matters. So I'm going to count each of those separately. Then I could get 3, 3, and 3, 6, and finally 6, 1, 6, 3, and the 6-child family twice. Okay, now that I have all of the possible 2-person samples, that is my complete sample space, I'm going to calculate the average family size for each one. So for this first sample, the average family size is 1 plus 1 divided by 2. That's 1. For the second group here, it's 1 plus 3 divided by 2. That's 2. 1 plus 6 divided by 2 is 3.5. See, you get the idea, right? So 4 plus 1 is 2. It gives me 2. 3, 9 divided by 2 is 4.5. 7 divided by 2 is 3.5. 9 divided by 2, and 12 divided by 2. Okay. Finally, I'm going to summarize those results over on the other side. Right? So let's see, what are my options here? I've got sample means of 1, 2, 3, 3.5, 4.5, and 6. Those were all the distinct values I got for the average family size in the sample means column here. And how many of each did I get? Right? Well, I got one family one sample whose average size was 1. And I want to do the frequency this here. So I have a total of 9 samples. So this would be 1/9. And I'm leaving a little room here. I'm going to make these into decimals in a minute. I have two samples whose average number of children was 2. So that's 2/9. I've got one whose average was 3, 2, 2, and 1 again. So if I make these into decimals, this is 0.11, this is 0.22, and I really only have two results here, right? I've got 1/9, which is 0.11, and 2/9, which is 0.22. When you do a quick check here, right, and that's going to show you something really interesting about this. So I want you to think about what we've done, right? This table lists all of the possible means for our population, all of the possible results, and the frequency or probability of getting each size if we selected 2 families at random. Now, if you think back to our definition several lectures back, what we have here is a probability distribution. It lists all the possible outcomes. The second column is the frequency of each result. And if you add all of those up, you should see that it does come out to 1. Actually, it comes out to 0.99, right? Because there was some rounding involved, and that's fine. So now, here's where it gets interesting. Suppose we calculate the mean of the distribution. Right? Remember how we do that when we have a probability distribution. We take each x value and we multiply it by its corresponding probability. Right? So 1 times 0.11 is 0.11. 2 times 0.22 is 0.44. 3 times 0.11, 3.5. You could have rounded that to 0.8 to 0.78. I'm going to leave it as 0.77. This one is 0.99. You could round that to 1. That'd be okay. And this one is 0.66 or 0.67 if you round. Now, remember how we get the final mean of the distribution? We add down this column. And if you do that, right? If you do that, when I did this, I did it in Excel, right? So there wasn't any rounding concerns. If you do that, you get 3.33. And that is the really cool part. Here's why. Go back to the original population. Remember, this is the entire population that I'm looking at here, right? What is the average family size of the population? Right? Well, to find the average family size, add them all up, 1 plus 3 plus 6, divided by 3, and that comes out to 3.33. You get exactly the same result, right? It's not a coincidence, okay? It's not a coincidence that the average, and just bear with me, right? It's these very long names. The mean of the sampling distribution of the sample means, right? That's this 3.33 is equal to the mean of the population. Okay, so what I want to do next, so what I've done here is I've got a very similar scenario. I just changed the numbers, 1, 4, and 5, just to make things a little more interesting. What I want you to do is I want you to repeat what I just did, right? But instead of doing this with the means, I want you to do the medians, right? So you're going to list all the samples. You're going to list the medians of each two-family sample. Then you're going to calculate the sampling distribution of the sample medians and see what you come up with. Okay, so my samples are going to be 1 and 1, 1 and 4, 1 and 5, 4 and 1, 4 and 4, 4 and 5, 5 and 1, 5 and 4, 4 and 5. And I need the medians. Remember, we have the data sets are very small, but I do have more than one element. I've got 2. So remember, we're going to find the median by averaging these two numbers. So 1 plus 1 divided by 2 is 1. 1 plus 4 divided by 2 is 2.5. You can keep doing this, right? 3, 2.5, 4, 4.5, 3, 4.5, and this one should have been 5, 5, right? So that's going to be 5. All right, now let's make our sampling distribution. All right, what are the different medians that I got? Well, I got 1. I got 2.5. Let me put the frequencies in here at the same time. This is 1/9. This is 2/9. Who's next? 3. That's 2/9. And then 4. That's 1/9. 4.5 is 2/9, and 5 shows up once. So these are, we saw these before, right? The 1/9 are 0.11, and the 2/9 are 0.22. Now multiply across, right? Do x times p. This is 0.11. Let's see, 2.5 times 0.22 is 0.55, 0.66, 0.44, 0.22 times 4.5 is 0.99, and 0.55. Now, add all of these up, and you get 3.3. So this is the mean of the sampling distribution of the sample medians. Go back to the original data set, or go back up here to the population. What's the median of the population? Well, now this is nice. I've got an odd number. The median is just the number in the middle, and you notice that it's different. This does not always work. Okay? Doesn't always, you're not always going to get a match. All right, so we have language to describe this. Right? We use this word target. All right? The mean of the sampling distribution of, and you notice I've listed 3 things here, right? Variances, proportions, and means is equal to the population variance, proportion, or mean. In other words, the word we use here is targets. The mean of the sampling distribution targets the population value, targets the population parameter for these 3 statistics. Don't assume, and there's other ones where it'll work for. These are the 3 that we're going to focus on. Don't assume that it does for other ones, because as we just saw, right, it does not work. It does not target the population median. Okay, so two more definitions here, right? An estimator is a statistic used to infer the value of a population parameter. That's what we've been looking at here, right? We can use the statistic, the population mean, to infer the value of, we can use the mean of the sampling distribution to infer the mean of the population, right? And an unbiased estimator is a statistic that targets the value. In other words, an unbiased estimator is one that equals the corresponding population parameter. Okay, so what's next? Next, we're gonna do some calculations, right? We're gonna see how we can take this idea and use it to actually answer things like that probability question I had on the first slide. We were asking about the probability of the average size of a group being in a certain range.